everyone, this is Sravanthi, Assistant Professor, Department of Chemistry in Institute of Aeronautical Engineering. Today we are going to discuss about the topics are factors affecting rate of corrosion and corrosion control methods. So, which factors affecting rate of corrosion? First we'll discuss what is corrosion. Corrosion means loss of metal by attacking environmental conditions or atmospheric gases on metal surface is called corrosion. The best example is rusting of iron. When iron metal interacts with atmospheric oxygen, then form iron oxide. So this is called rusting of iron. That means loss of metal by attacking environmental conditions or atmospheric gases. So what are the main reasons of corrosion? Generally metals available in nature in the form of metal oxide, metal sulfides, metal nitrates, etc. These are called ores. But our own purpose, we extract the metal from these ores or mineral compounds. So the natural tendency of metal always try to get their original position is called corrosion. So now let's discuss which factors affecting corrosion, rate of corrosion. So there are two types of factors affecting rate of corrosion. One is nature of metal and the one is nature of environment. So in this nature of metal, mainly purity of metal, physical state of metal, nature of oxide film, that means metal oxide layer, and position of metal in galvanic series, relative areas of anode and cathode, and solubility of the product of corrosion, and electrode potential, which are related to nature of metal, mainly effects on rate of corrosion. And now we'll discuss nature of environment. In this we are going to discuss temperature, humidity of air, pH value, conductance of the corroding medium, and presence of suspended particles or impurities which are present in atmosphere, and amount of oxygen in atmosphere. So these are the factors affecting on rate of corrosion. So in this first we'll discuss nature of metal. First one is purity of the metal. So 100% pure metal doesn't undergo corrosion. That means, for example, here zinc metal. Generally it is undergoes corrosion, but the process is slow starting. If in case any small impurities like iron or anything, small impurities present on it, the rate of corrosion will be increases. That means it develops galvanic cells. So purity of the metal means 100% pure metal doesn't undergoes corrosion. If in case any impurities present on it, it is fastly increases. The rate of corrosion is increases fastly, rapidly. And next, electrode potentials. So generally the metals which are higher reduction potentials, so which are having high positive reduction potentials, so doesn't undergoes corrosion easily. For example, noble metals like gold, platinum or silver. So these metals, these are having high corrosion resistance, so does not undergoes corrosion easily. But the metals which are having lower reduction potential, that means anodic nature, so these metals easily undergoes corrosion. So electrode potential also clearly affects on this rate of corrosion. So metals which are having high positive reduction potentials or reduction potentials, those metals undergoes corrosion is very less chances compared to which are having anodic nature. Next, third one is position of metal in galvanic series. So the position of metal also in galvanic series affects on this rate of corrosion. So for example, metals which are higher position in this electrochemical series or galvanic series, so those metals all are having anodic nature, that means less reduction potentials, and those metals are having high oxidation potential. So those metals easily undergoes corrosion. For example, zinc metal. So this metal is generally in a galvanic series, it is above the position of hydrogen scale in this electrochemical series also. So this metal is having high positive reduction potential. So that means, high oxidation potential. So it is easily undergoes corrosion. So in this, the rate of corrosion depends on the difference in their position in the galvanic series. So greater the difference, more will be the extent of corrosion at anode. For example, here zinc and copper. So zinc is present above the series and copper is presented below the series in this galvanic series. So zinc is having high oxidation potential, that means less reduction potential. Copper is having high reduction potential, less oxidation potential. So when we couple this zinc and copper, so obviously zinc present in higher position in electrochemical series or galvanic series, so easily undergoes corrosion. So position also affects this rate of corrosion. Next, relative areas of anodic and cathodic cells. So relative areas of anodic and cathodic cells means if the metal has small anodic area, large cathodic area. If the metal has small anodic area and large cathodic area. So in this case, the rate of corrosion will be more compared to large cathodic area and small anodic area. For example, in the wet corrosion, absorption of oxygen. Absorption of oxygen. So when the iron metal, it is interacts with atmospheric oxygen, then form iron metal oxide layer. If in case any impurities present on this metal surface, it getting cracks. If in case any impurities present on this or any atmospheric factors affecting, so it get this metal oxide layer getting cracks. So that cracking part acts as anode and rest of the part acts as cathode. So in this case, it develops small anodic area and large cathodic area. So in this case, rate of corrosion is increases rapidly. It easily undergoes corrosion. Rate of corrosion is more. For example, evolution of hydrogen by wet corrosion. So in this case, when the metal, for example, here we are taking iron metal, when it is contact with acid solution. Okay, so in this case, iron metal undergoes oxidation, then gives iron metal ions and loss of 2 electrons. So in this case, this is acts as anode. So at which area, when it is contact with acid solution, at which area hydrogen displaces from acid solution and move to the surface area. That area acts as cathode. So at cathodic area, it is present hydrogen ions. So in this case, rate of corrosion is less compared to this absorption of oxygen, because in this case, it's present more small anodic area, large cathodic area. But in this case, large anodic area, small cathodic area. So in this relative areas of anodic area and cathodic area means here, if in case the metal has small anodic area and large cathodic area, so in this case rate of corrosion is very high because the electrons are liberated at anode, which is consumed at cathode. That is the main reason. Or otherwise, if the cathodic area is larger, the liberated electrons are rapidly consumed at cathode. So in this case, this further enhances the anodic reaction, leading to increase the rate of corrosion. Next, physical state of metal. So physical state also mainly affects the rate of corrosion. Okay, so physical state means the grain size is small. It is easily soluble in this corroding medium. So that means rate of corrosion also increases. And next one is nature of surface film or metal oxide layer. If the corrosion product means here metal oxide layer, it forms stable metal oxide layer. For example, here this is the metal where it is interacts with, for example, oxygen, then form metal oxide layer. So this metal, when it is reacts with the oxygen, atmospheric oxygen, then form metal oxide layer. If this metal oxide layer is stable, so in this case it acts as protective. That means non-porous and insoluble. So which type of metal forms a stable metal oxide layer? So here titanium, aluminium or chromium. So these metals when interacts with atmospheric oxygen then form stable metal oxide layer. That means these are insoluble and non-porous. So in this case it acts as protective. So if the, for example, if the metal when interacts with atmospheric oxygen then form metal oxide layer, it is unstable. That means it is having pores, or it volatilizes, or sudden changes occurs on this metal oxide layer. So in this case, it is metal oxide layer acts as non-protective. For example, alkali and alkali earth metals. When this metal interacts with atmospheric oxygen, then these metals are this metal oxide layer is unstable. So in this case, it is easily undergoes corrosion. For example, the alkali or alkali earth metals like calcium or magnesium, where it is interacts with atmospheric oxygen, then form metal oxide layer. If in case any reason or stress, strain or any other atmospheric factors affecting on this, so it is decomposed back into metal and oxygen. That means it forms non-porous layer. This nature of surface film means it is under which metal oxide layer is acts as protective or which metal oxide layer is acts as non-protective. It is clearly explained also by Pilling Bedworth rule also. This Pilling Bedworth rule also clearly explain which type of layer is protective on metal surface or which type of metal oxide layer is non-protective. So according to Pilling Bedworth rule, the volume of oxide is greater than volume of metal. The oxide is more than metal. In this case, that metal oxide layer is acts as protective. That means it doesn't undergoes corrosion. That metal doesn't undergoes corrosion. Or otherwise, the volume of oxide is less than the volume of metal. In this case, that metal easily undergoes corrosion. So this metal oxide layer also affects on this rate of corrosion. Now discuss nature of environment, second type of factor is rate of corrosion. So in this first one is temperature. So rate of corrosion reactions increases with increasing in temperature. That means temperature is directly proportional to the rate of corrosion. The temperature increases, corrosion also increases, or temperature decreases, corrosion also decreases. So rate of corrosion reaction increases with increasing in temperature. Next, humidity in air. Humidity means it is nothing but a moisture present in atmosphere. So generally you know that humidity increases means corrosion, rate of corrosion also increases. Or humidity decreases means rate of corrosion also decreases. Next factor is pH value. So pH value of the medium, it has a greater effects of the corrosion. The most acidic medium of or acidic pH, it increases the rate of corrosion compared to basic or neutral medium. So how can we avoid this one? So increase the pH of the electrolytic medium or corroding medium, because acidic medium easily undergoes corrosion compared to basic or neutral medium. That means below 7 is an acidic medium, considered as acidic medium. So increase the pH, we can protect from corrosion, those type of metals. And next, presence of impurities. If any impurities present on metal surface or any suspended particles present or in atmosphere any other gas is present, so when it interacts with the metal, it is easily undergoes corrosion and the rate of corrosion is more. That means it develops electrochemical cells or heterogeneity creating. That means this metals, if in case any impurities present on metal surface or interacting with metals, easily undergoes corrosion. That means rate of corrosion is increases. The next one is amount of oxygen in atmosphere. Generally in atmosphere, oxygen percentage increases means corrosion, rate of corrosion also increases. So here it is due to the formation of oxygen concentration cell. So in the case of metal occurs at the anodic part and the cathodic part of the metal is to be protected. Simply we say if in case oxygen percentage increases in atmosphere, so the rate of corrosion also increases. So these are the factors affecting on rate of corrosion. One is nature of metal and then one is nature of environment. So now let's discuss corrosion control methods. In this mainly discussed about this cathodic protection. It is also called as electrochemical protection method. Electrochemical protection method or cathodic protection method. So in this type of corrosion, the main principle involved in this method is to force the metal to behave like a cathode. So in this corrosion control method, mainly discussed about this cathodic protection method. It is also called as electrochemical protection method. The main principle involved in this method is to force the metal to behave like a cathode, because corrosion always concentrated anodic area. So the cathodic area only reduction reactions takes place but do not affect the cathode. So always in this method, the main principle is to force the metal, and wantedly we converted anodic metal to cathodic metal because corrosion always concentrated anodic area. So the basic metal acts as generally cathode, it to be protected from corrosion. That is the main principle involved in this cathodic protection method. So there are two types of cathodic protection methods are there. One is sacrificial anodic protection method and second one is impressed current cathodic protection method. So first one is sacrificial anodic protection method. So what is the meaning sacrificial anodic protection method? So anode is sacrificed to protect the base metal from corrosion. Here base metal means which metal we can protect it from corrosion, that is called base metal. So here sacrificial anodic protection method means anode is sacrificed to protect the base metal from corrosion is called sacrificial anodic protection method. So in this method, the basic metallic structure which we can protect it from corrosion. So the basic metallic structure, it will be protected to behave like a cathode because always corrosion concentrated anodic area only. So the basic metallic structure to be protected to behave like a cathode by connecting it with more active metal. Generally this more active metal means easily undergoes corrosion. And here this more active metal acts as anodes, sacrificial anodes. So basic metallic structure which we can protect it from corrosion, wantedly we connected with more active metals which are acts as anode. So that the corrosion will concentrate only on this more active metal, that means anodic part or anodes. So the artificially made anode thus gradually gets corroded, protecting the original metallic structure. So hence this process is known as sacrificial anodic protection method. Generally used sacrificial anodes are aluminium, zinc, magnesium. These are used as sacrificial anodes. So for example here, this is a basic metallic structure, that means which you can protect it from corrosion. For example here you are taking iron pipe. So it can be, generally this iron pipe when it interacts with atmospheric oxygen or any other impurities, then easily undergoes corrosion. So actually it acts as anode. But in this method, wantedly we connected with more active metal like zinc or magnesium sheets. Here you are using magnesium. Wantedly we connected with magnesium sheets. So in this case, this magnesium is more active than iron. So corrosion always concentrated this anodic area. So obviously it acts as cathode. So what is the concept here? Sacrificial anodic protection method. Anode is sacrificed to protect the base metal from corrosion. For example here, iron pipe, this is protected from, for example, soil corrosion. So wantedly we connected with this more active metal like zinc or magnesium sheets. Here I am taking magnesium sheets. So in this case, the magnesium is compared to iron, it is more active metal. So in this case, it acts as anode. So the basic metallic structure is protected and acts as here cathode. So this method is called sacrificial anodic protection method. So important applications of the sacrificial anodic protection method. So protection of underground cables and pipelines from soil corrosion. Protection of underground cables and pipelines from soil corrosion. Underground cables and pipelines means the pipelines are the basic metallic structure connected with sacrificial anodes like zinc or magnesium sheets. So in this case, corrosion concentrated anodic area. So this basic metallic structure we can protect it from corrosions. So for example here, protection of underground cables and pipelines from soil corrosion. And one more application is protection of ships and boats from marine corrosion. Protection of ships and boats from marine corrosion. For example, here the hull of the ship is part made up of iron. Hull of the ship made up of iron. Generally, it is undergoes oxidation. But wantedly, when we connected with or zinc or magnesium sheets hanging around the hull of the ship, zinc or magnesium sheets hanging around the hull of the ship. So in this case, corrosion concentrated is more active sheets or metals. So corrosion concentrated more active metals. So in this case, the rest of the part, this part acts as cathode. So in this method, main applications of the sacrificial aeronautical protection method is protection of underground cables and pipelines from soil corrosion, and one more application is protection of ships and boats from marine corrosion. And one more application is prevention of rusty water by inserting magnesium sheets or rods into domestic water boilers or tanks. Already we know that zinc and magnesium more active than this iron pipes or wires. So that means more active metal easily undergoes oxidation. So wantedly we connected with this more active metal to basic metallic structure. So corrosion concentrated more active metals. So basic metallic structure protected from corrosion. So this method is called sacrificial anodic protection method. And second method is impressed current cathodic protection method. So in this method, impressed current is applied. So impressed current is applied opposite direction of the corrosion current. So what purpose we supply impressed current to opposite direction of corrosion current? Because to cancel out the effect of corrosion on basic metallic structure. So this is called impressed current cathodic protection method. So in this case, anodic metal converted to cathode when we supply impressed current opposite direction of the corrosion current. So it can be done by negative terminal of the battery connected to this basic metallic structure. Basic metallic structure means which we can protect it from corrosion. So in this negative terminal of the battery connected to this basic metallic structure which we can protect it from corrosion, and positive terminal of the battery connected to this inert anode. Generally in this impressed current cathodic protection method, used anodes or inert anodes used for this purpose is graphite, platinized titanium. Graphite, platinized titanium. For example, here, this is the iron pipe wantedly connected with, here see, negative terminal of the battery connected to this basic metallic structure and positive terminal of the battery connected to this inert anode. So inert anodes means here we are using platinized graphite, platinized titanium. These are stable. So negative terminal of the battery connected to the basic metallic structure which we can protect it from corrosion, and positive terminal of the battery connected to this inert anode. So in this case, from this battery, it provides electricity, impressed current to pass opposite direction of the corrosion current. That means it produces electrons opposite direction. So at cathodic area, this metal gain of electrons and deposited there as at cathode. So at anodic area, so these electrons produced from this inert anode. So inert anode is kept buried in this backfill. See here, for example, this is the iron pipe. When it is connected with inert anode, here negative terminal of the battery connected to this basic metallic structure and positive terminal of the battery connected to this inert anode. Okay, so here when we pass impressed current is applied opposite direction of the corrosion or basic metallic structure. That means it produces electrons opposite direction from this battery. So electrons produced means these electrons gained at cathode, because cathodic area reduction reactions takes place. Reduction means gain of electrons. So then this anodic metal converted to cathode. So here, for example, here this is the iron pipe. When it is connected with negative terminal of the battery connected to this basic metallic structure, that means iron pipe, and positive terminal of the battery connected to this inert anode. And next, this inert anode is buried in or kept in this backfill. The here backfill means is the mixture of gypsum, coke, grease, or sodium sulfate. So what is the use of this backfill? So it provides good electrical contact to anode. So in this impressed current cathodic protection means impressed current is applied opposite direction of the corrosion current. That means cancel out the effect of corrosion on base metal by supplied electricity opposite direction. So in this purpose, we are using anode is platinized titanium, graphite platinized titanium acts as anode, and basic metallic structure is which you can protect it from corrosion. So this inert anode is kept in this backfill. It provides good electrical contact to this anode. So what are the applications of this impressed current cathodic protection method? So this method also used for protection of pipelines, cables from soil corrosion, and also used for ships and boats from marine corrosion, and also used for protection of structure of structures like tanks, pipelines, transmissions like towers, underground water pipelines, oil nets, ships, etc. We can protect it from by this method. Next, what are the difference between sacrificial anodic protection method and impressed current cathodic protection method? These two methods are used for protect the base metal from corrosion only. So here sacrificial anodic protection means anode is sacrificed to protect the base metal from corrosion. But in this impressed current cathodic protection means we supply power or electricity opposite direction of basic metallic structure. So in this case, it cancels out the effect of corrosion on base metal. And next, so what are the differences between these two methods? So first one is, in the sacrificial anodic protection method, external power supply is not required. We cannot supply any external power. But in this impressed current cathodic protection method, external power supply is compulsory, it is required, produced from this battery. So power supply is required. And the cost of investment is low in this sacrificial method. But here, the cost of investment is high. And it requires periodic replacements of sacrificial anodes. And we are using different types of anodes like more active metals like zinc, magnesium, aluminum, etc. We are changing, depends upon this basic metallic structure. But here, replacement is not required. Anodes are stable, just as discussed already. In this impressed method, we are using generally graphite titanium, graphite platinized titanium used as a fixed anode, inert anode in this impressed current cathodic protection method. Graphite platinized titanium used as inert anode. And next one is soil and microbiological corrosion effects are not considered in the sacrificial anodic protection method. But here, soil and microbiological corrosion effects are taken into account. We can consider these effects also. And next one, this is the most economical method, especially when short-term protection is required. And here, in this is well suited for large structures and long-term operations, stable, using for long period also. And last one is, this is a suitable method when the current requirement and the resistivity of the electrolytes are relatively low. But here, this is suitable method even when the current requirement and the resistivity of the electrolytes are high. In this case, we are using this impressed current cathodic protection method. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.